Hi guys, in this video we're going to work through some cross product problems. In particular, we're going to look at computing a cross product given u and v in component form, and then we're going to show that the cross product is perpendicular or orthogonal, to both u and v. So we're going to demonstrate this first property, and then we're also going to look at a couple of area problems. And then we'll save the physics and the volume here for another video. So let's just do this one. I want to find u cross v, so I'm going to use determinant form. So I create this 3x3 determinant form. I list the components of u in the second row and the components of v in the third. And then we cross out the row and column containing I hat. And I'm not going to show the 2x2 determinants. I'm going to do it in my head. But I did show the 2x2 determinants in the first video, so you might want to check that out if you're not comfortable doing this part in your head yet. So we cross out the row and the column containing I hat, and you see that 2x2, and then you evaluate that 2x2 determinant. So you multiply across this diagonal, 6 times 1, and then you multiply across this diagonal, 1 times 0, and you subtract. That's times I hat. And then you're always subtracting from that the 2x2 determinant that you get after you cross out the row and column containing j hat. So it's plus minus plus. So we're going to cross out the row and column containing j hat, and I'm left with this 2x2. Multiply across this diagonal first, so I've got 1 times 1 is 1, minus 2 times 0, which is 0. And then we're going to cross out the row and column containing k hat, and we'll evaluate that 2x2 determinant. So you do 1 minus negative 12. Subtracting negative 12 is the same as adding 12. Okay, so it turns out that u cross v is the vector with components 6, negative 1, and 13. Now I could try to draw these for you, and then we could try to visualize, try to imagine how this vector is orthogonal to both of these two vectors, but it's easier to show that it's orthogonal using the dot product. Remember, we want to, whatever u and v are, wherever they point, the cross product is perpendicular to both of them. U cross v points up and the v cross u points down if u is that way and v is that way. So this is perpendicular to this vector and this vector. To check, I keep saying perpendicular. I'm talking about vectors, so they're orthogonal. To check, we can just take the dot product. So we want to show that u cross v and u are perpendicular or orthogonal, same thing, and u cross v and v or orthogonal or perpendicular. And we know that two vectors are orthogonal if their dot product is 0. So I'm going to take u cross v, and then I'll dot it with u, and hopefully I'll get 0. So I have 6, negative 1, 13, and I'm dotting that with u, which is 1, 6, 0. So I get 6 times 1 plus negative 1 times 6 plus 13 times 0. So I have 6 minus 6 plus 0, which of course is 0. So this is orthogonal to this, which is good. Now we also want that to be orthogonal to v. So take our cross product and compute its dot product with v. V was right there. Remember how we do dot products. You multiply and add, multiply and add, multiply and add. We're hoping we get 0. We've got negative 12 minus 1 plus 13, that sure is 0. Okay, so it turns out that the cross product of u and v is orthogonal to both u and v, which means if I make a plane like this, it looks like this. U cross v is just pointing out of the plane at a 90-degree angle. Okay, so now let's look at some area problems. So let's say that A is the point 0, 3, 2, B is the point 1, 5, 5, C is the point 6, 9, 5, and D is the point 5, 7, 2. We're asked to verify that the points form the vertices, or are the vertices, excuse me, of a parallelogram. And then we want to find its area. Now, one struggle with this is you're really not sure which sides or which points are where. So I might assume, I might assume that this is A, B, C, and D, but I might be wrong. Like I might end up accidentally, creating a vector from one point over here, like across the diagonal of the parallelogram. That's not what I want to do. So we need to compute some vectors here and see which ones are parallel to each other. So I'm going to compute a vector from A to B and see what that gives us. So the vector from A to B can be written this way. You start with the coordinates of B and you subtract the coordinates of A. So you get 1, 2, 3. Okay, that's cool. Are there any other 2 points that create a vector 1, 2, 3, so that they'd be on opposite sides of our parallelogram? Well, I think I see that right there. There's C to D. To go from 5 to 6, I'd have to go up 1. To go from 7 to 9, I'd have to go up 2. To go from 2 to 5, I'd have to go up 3. So it looks like it's C minus D, so C is my terminal point, so this is DC. So I've got 6, 9, 5 here, and we're going to subtract 5 and 7 and 2. And so I get 1, 2, 3. That's cool. So A is here, and B is here, my cartoon, and that's the vector 1, 2, 3. And that's parallel to the vector DC, which also has component form 1, 2, 3. So now I'm hoping that BC and AD are also parallel to each other. So let's do AD and see if it's the same as BC. So for AD, I take the coordinates of D, 5, 7, and 2, and I subtract the coordinates of A. So I subtract 0, 3, and 2. So I get 5, 4, and 0. Okay. So that was AD, 5, 4, 0. Hopefully BC is the same. 1, I start with C. 6, 9, 5, and I subtract the coordinates of B, 1, 5, and 5. I get 5, 4, 0 again. Awesome. All right. So we do have a parallelogram. I'm going to call this vector the vector U. I'm going to call this vector the vector V. We have confirmed it's a parallelogram because AD or AB is equal to DC, and AD is equal to BC. So we definitely have a parallelogram. Now we want to find its area. And I'm going to call AB the vector V and AD the vector U. Now, according to our formulas, area of this parallelogram is the length of the cross product. Now I could compute the cross product and then compute its length. That's one way of doing this. Or we could find the length of U and then the length of V and then find the angle between them. In order to find the angle between them, we'd have to use the dot product, and then we need to take the sine of it. It sounds like a lot of work. I think I'd rather just take the cross product and then find its length. So I'll do that instead. First, find the cross product. So U had components 5, 4, 0, V had components 1, 2, 3. So now we are going to cross out the row and column containing I hat, evaluate this 2 by 2 determinant. So we do 12 minus 0. That's our x component, minus for the j hat, for not j hat, for the y component. So we cross out the row and column containing j hat, and we get 15 minus 0. And then cross out the row and column containing k hat, we get 10 minus 4. All right. Area of the parallelogram is the length of this vector. So you take the components, you square them, and add them, and take the square root. Now I'll use my calculator for the arithmetic. I got the square root of 405, or 9 times the square root of 5. And its area, so it's some number of units squared. That's the area of this parallelogram. Now if someone said, find the area of the triangle with A, B, and C as vertices, the area of the triangle is just this area right here. So first I'd find a vector from A to B, and then I'd find a vector from B to C. And once I have those two vectors, U and V, then I can do exactly what I did down here. The area of the triangle is going to be 1/2 of the length of the cross product of U and V. You'd still find U and V the same way that you did before. Just find a vector from point to point and another one from point to point, and then just take that cross product, find its length, and then because we're talking about the triangle, now we divide the length, or divide the area of the parallelogram by 2 to get the triangle. So we have 9 square roots of 5 over 2 units squared. So that's our area application.